So my plan here for today, I'll talk a little bit about test format, what to expect. We'll take some questions, but largely this is going to be like a day of review stuff. Cool with the plan? Okay. So I'm looking in the content library right now. So this is the test 1 tab. So your test is going to be 2 parts. So part 1 is no calculator. So I want to say part 1 is no calculator. Part 1, you'll have 10 multiple choice questions, which will look similar to the things that you saw in the MCQ practice that I gave you guys. There's like 40 or something in there to play with. And then 1, what I'll call like a free response question, like a normal question like I would have written. And then part 2, calculator is allowed, and you'll have 7 limit questions and 1 like free response question. So again, like, a question I would have written. So skills that you'll need to be able to demonstrate: use a graph to determine a limit, use a table to determine a limit, use algebra to determine a limit. Remember the techniques we've looked at for that would be direct substitution, or if it's indeterminate, you might be able to FOIL and simplify and then do a direct substitution, or factor and reduce and then do a direct substitution, or multiply by a conjugate, reduce and then do a direct substitution. The absolute value one, remember we did one there where you have to look at the pieces for the absolute value functions, a little tricky. And then you'll use like your limit at infinity techniques from 2.6. You should be able to apply the squeeze theorem to determine a limit. Apply the intermediate value theorem to show a function takes a specific value. Use a limit to show a function has either a vertical or horizontal asymptote. Should know the 3 types of discontinuity and be able to identify them from a graph or table or limit, etc. So again, those 3 types are removable, jump, and infinite or vertical asymptote. You can demonstrate whether a function is continuous or discontinuous at a specific x. Again, you're doing that using the definition of continuity. And then know which types of functions are continuous over their domains. Basically everything from algebra 2 and trig. So in addition to the skills above, you can, if you're looking for practice from my APs, like you can look at the Unit 1 multiple choice practices. There's some stuff I ask you to, that you could skip. Some problems from the homework that we've already done that I think would be similar to things, or at least things that I would have looked at when I wrote my own questions. So these are things that would be inspiration for things from the test. Do you guys feel okay about format-ish on kind of what to expect? Okay. I promise we're going to talk about test date too, I think, right? Let's do that. Tentatively, I had planned for Thursday this week. Is there strong objections to doing Thursday? Other than the people that are gone on biology, I think a couple of people have talked to me about being gone, and you make it up whenever you're back. It's not I'm not.
Let's take that for 80 minutes. It's a mass day on Thursday.
Thursday's a mass day?
Yeah.
Why is there Thursday on mass? Oh, don't we have mass on this Friday also?
No,
Just Thursday? That's so weird. Okay. Well, that is a fair issue. Yeah, so I don't want it to be rushed. We'll do it, I guess, next week then. That's a real thing. Like, I don't want you guys to panic. I wrote this as an 80-minute. So let's make it 80 minutes, right? So Monday the 16th then is the date?
Yeah.
Okay. That's fair. We'll just start the next stuff on Thursday then. Or if you'd rather wait and do the review stuff on Thursday, we can just start the next stuff now. What are our thoughts? So I'm asking, since we're moving the test off of Thursday since it's mass, I was asking if we'd rather do the review day today or do that on Thursday. Okay, so I'll just start then the next stuffs today. Okay. Last time I was here, we looked at section 2.1. I think I dropped in the filled out version and I did not. Okay. Did we have any questions from the 2.1 stuff? On Friday, I left the 2.1 stuff to the video to watch. I asked you to watch that and work on the 2.1. There's like 5 problems or something. Basically just turned into doing slopes, right? That was the takeaway. Okay. All right. So if there's no questions there, we'll go ahead and start in on 2.7 then. So these two sections, 2.7 and 2.8, are going to be very important going forward. In these two sections, we're going to be like defining and developing the idea of a derivative, which we'll be using throughout the entirety of the rest of first semester. So remember we talked about there being kind of like 3 big thing or types of problems or operations that we're going to see in calculus: the limit, the derivative, and the integral. So first semester is largely concerned with just like limit and the derivative. Second semester largely concerned with the integral. So this will be a major thing that we see going forward. So last time we talked about finding like this, like a secant for a function, right? Where you're basically just doing a slope. We're calculating the average value, right? Which again was just a slope. But what happens if I want to find the slope at like one specific point? Like what if I want to find the slope at this point P exactly? Now I can't use the slope formula with just one point because I end up with 0 over 0, right? So what do we need to do here? Well, the idea is we're going to start with a secant line. So I'm going to pick some arbitrary other point Q. So if I calculate the slope, that's going to be Jack Karazak. It's for you. And I calculate the slope. I'm going to have something like f of x minus f of a over x minus a, right? And then what I'm going to do is I'm going to let that point Q get progressively closer and closer to point P by taking the limit, right? We're going to look at the limit of that slope as Q approaches P. Everybody's okay with that idea? So every time we do that, I'm getting like different slopes until I get exactly there. And then that slope of that new line would be the slope at P. So let's define what we did here formally. So we say the tangent line to the curve y equals x at the point P, that is a comma f of a, is the line through P with slope equal to the limit as x approaches a of f of x minus f of a over x minus a, provided that limit exists. What do you notice about the problem with evaluating this limit using the methods we have so far? If you do a direct substitution, you're going to end up with 0 over 0, right? An indeterminate form. So we know that this is going to be, in general, this will be some like algebraic hurdle to get through so we can get past that indeterminate form. Everybody's okay with that plan? Okay. Or another way to look at it, I could write it as the limit as h approaches 0 of f of a plus h minus f of a all over h. Let's see why that form is equivalent. So let's say here is my P. Here is my point Q, that's just some h, distance h away from A, right? So just further down. So it's the point A plus H, comma, f of A plus H. So if I look at the change in y's, that's f of A plus H minus f of A. And the change in x's would be A plus H minus A, or just H, right? So this is equivalent to the previous one. It's still just slope, where my point Q is just some H units now to the right down the curve. Everybody's okay with that idea? Okay, so let's do some practice now. Example 1 says, find the equation of the tangent line to the parabola at y equals x squared at the point P11. So remind me again, going back to like algebra 1, what do I need to write the equation of a line? Or a point and a slope, right? I have one point already, and I have an equation above that I can use to calculate slopes, right? So let's do that. So it doesn't matter which form I use. I'm going to use this one, though, as I think it's the more common application. Yes, sir? Sure. So in this problem, my A is what value? It's 1. So this is going to be the limit as h approaches 0 of, and my f is x squared. Oops. A plus h squared minus f of a, or a squared over h. Is everybody okay with how I filled that in? Can I do a direct substitution here? Nope. What should I do? How about I just FOIL this out and see what happens? What do you think? I don't see anything other better ideas to do. So if I FOIL that out, I get h squared plus 2h plus 1, and then I have a minus 1. And that looks pretty good to me, right? What do you notice there in the numerator? The 1's cancel, and after the 1's cancel, what can we do? Yeah, I can take out an h and reduce it, right? And now I can do a direct substitution and just plug 0 in for h. So far, so good. Now let's write our equation for our tangent line. So I'm going to use the point slope equation for a line since I have a point and a slope. And that'll do. Is everybody okay there? Yes.
So the limit is just the slope.
So the slope is the limit. We'd say it that way. So the slope for our tangent line will always be that limit. But that's the big takeaway here. Now, historically, where this comes from, calculus was developed by, well, really two mathematicians kind of simultaneously, but the person who widely gets credit is Isaac Newton. He developed calculus in order to describe gravity and how gravity works. Specifically, he's looking at what's the rate of change in speed for a falling object, aka its velocity. Now, he could do this on average if you just take an object that falls from here to here. I can time how long it takes and measure the distance, and I can calculate a velocity, right? But what if I wanted to know, exactly right here what its speed is? That's what this is being done for, right? Is an instantaneous velocity is why he created this. Now, a lot of these ideas existed prior to Newton, but he saw the application and formalized a lot of this, even though the methods we use now are not Newtonian at all. He did everything geometrically, which is just kind of a nightmare. Actually, of all of our notation and stuff we use is come from the German who did develop the same thing at a different independent of Newton. Leibniz is his last name. There's a big battle in academia over who got credited for this, and Newton kind of won that battle. But Leibniz lives on because we use all of his notations. Anyway, continuing on. So next thing we're going to do, find the equation for the tangent line to the hyperbola, y equals 3 over x at the point 3, 1. So again, my a is 3, and then my f of x is 3 over x. So we have f of a plus h minus f of a all over h. Is everybody okay with how I set that up? What do we notice if we do a direct substitution? 0 over 0. Blah! So what am I going to do? You could go that route, and that'll work. I would suggest doing something different that's a little less messy, but that'll work for sure. That's a great idea. Equivalent to doing that is I'm just going to essentially clear the denominators out of this complex fraction. So first thing, I'm just going to think about 3 over 3 as just 1, right? So the only denominators are 3 plus h and 1 in the whole fraction. So that least common multiple of all those denominators is just 3 plus h. So I'm going to multiply the top and bottom by 3 plus h over 3 plus h. When I multiply it to the first fraction, I'm left with just 3, right? Everybody's okay with that? When I multiply to the second fraction, I'm left with 3 plus h. And when I multiply to the denominator, I have h times 3 plus h. Everybody's okay there? Notice I didn't bother to FOIL out the denominator. Typically, I'll never do that because I'm always going to be looking to reduce later on. So I need it in a factored form to do that, so I just never bother with FOILing out denominators. Almost never. So far, so good. What do you notice happens in the numerator? I can distribute that through and cancel stuff off, and I'm left with just a negative h up top. Aha! So now I can do a direct substitution. I just get negative 1/3. And now I'll just have to write my equation for my tangent line. So y minus y1 equals m times x minus x1. You see that I use the point slope formula almost exclusively, unless they ask for like a y equals mx plus b equation. I'm not giving you one because, like, why would I bother? Cut down to my algebra. So far, so good. Okay. So vocab, some vocab. If we talk about average velocity, that's just slope. Instantaneous velocity is that slope of the tangent line, right? Average is a secant line. Instantaneous is tangent line, aka average velocity slope, instantaneous whatever, derivative. Everybody's okay? And we'll formalize what we mean by a derivative here in a moment. Right now we just talked about slopes of tangent lines. Everybody's cool with that vocabulary? AP loves to use the terms average and instantaneous, just to make sure you really catch on. So I want to hammer that here a little bit. All right. Suppose a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. And we're asked, what is the velocity of the ball after 5 seconds? And then how fast is the ball traveling when it hits the ground? Physics people. Anybody here in physics? Yeah, lots of you are. Excellent. Got a falling object. What's our motion equation for a falling object? In meters. Right? Oops. Everybody's okay with that? Physics people? I wouldn't expect that you memorize this. This is just me quizzing you. Does that look right?
I don't think we've done that yet.
Oh. Well, guess what? When you do, you'll be like, already. Again, everyone else would not expect that you know this off the top of your head. This is just me picking on the physics people. I would give you the equation. Okay. So if I want the velocity after 5 seconds, I want this, right? V of 5, which will be the limit as h approaches 0 of, let's change that to s of t, s of 5 plus h minus s of 5 over h. Everybody's okay with that idea? So I use my position function to figure out the velocity, the instantaneous velocity. So plugging things in. What did I do wrong? Who sees it? Mr. Kulik made a mistake. Look at it. Nobody sees it? Somebody's got to. Makes me nervous about your test if nobody sees it. I forgot to write limit. Yes. Great job. Yeah. I need a limit here. I haven't plugged anything in yet. That's a real mistake. It's not like a, it's a real mistake still. Everybody's okay? Okay. All right, now that we got that, what should I do next? I still can't do a direct substitution, right? Because I get 0 over 0. What should I do? Foil it out. Great. So I'm going to get 4.9 times 5 squared plus 4.9 times 10h plus 4.9 times h squared minus 4.9 times 5 squared all over h. Everybody's okay with what I did there, foiling? I didn't want to do the multiplication because quite frankly 25 times 4.9 I couldn't feel comfortable doing in my head. But I don't think I'm going to need to do it. At least until the very, very end. So those guys cancel, right? Oh, not those guys. Those guys cancel. Sorry about that. So far, so good. What do you notice? That we can do now? Yeah, we can reduce an h out of there. So I have 4.9 times 10 plus 4.9 times 0. So I have 49 meters per second. Feel okay? So far, so good? Yeah, Alex.
On the first part of the equation, are those s's outside of the?
Yeah, so that's like s of
Yeah.
a plus h, and then s of a. Yep. So that's a. Part B asks, how fast is the ball traveling when it hits the ground? So I need to do v of whatever the time it takes to hit the ground, right? So how far is the ball traveled when it hits the ground? 450. So that's going to be my S of t. And I'll just solve for t, right? So I divide both sides by 4.9 and I get 100. So t should be 10. Do you feel good there? Okay. So if I do v of 10 then, that's going to be the limit this, oops, right? Oh my goodness. Guys. Yeah, I look at this terrible looking 5. My penmanship's so bad I thought it was a 9. Great googly mooglies, guys. I apologize profusely. Okay. Okay. All right. Shh. What do you notice that I'm going to be doing now? Yeah, what kind of algebra? That's good. That's good. What kind of algebra, though, am I doing? Like, what are the steps going to look like? What are the steps going to look like? Not quite conjugates. It's going to be basically the exact same steps as the previous problem, right? Do you see that? Who thinks that stinks? That stinks, right? Why do I have to do the same steps over and over and over again? Let me propose a different approach.
Why can't you just solve what's the 450?
You could make it a decimal. I just don't want to take a calculator out and make a decimal out of it. Again, because part of the AP exam is no calculator, I'm always going to do any problem that can be done without a calculator without it first to demonstrate to you, like, what does this look like with no calculator before I go and revert back to a calculator. So I'm always going to go in that order. And then if you can do it with a calculator also and it makes it meaningfully different, I'll show you that. But so on a problem like this where I'm going to have to calculate like multiple different velocities for the same function, this would have been the better approach. Is what if we just did this once for an arbitrary A? So if I do this once for an arbitrary A, one, the numbers kind of make it a little bit easier. Oops, I need a 4.9 there. And so like cancel, cancel, reduce, reduce, reduce. So I get like 9.8a. Everybody's okay with that? So if I want v of 5, that's just going to be 9.5 times 5. If I want v of the square root of 450 over 4.9, that's just going to be 9.8 times the square root of 450 over 4.9. Whoa! Mr. Kool-Aid, that is a more efficient way of doing this because you've just like dramatically cut my algebra time in half. If I'm asked to do like a bunch of these slopes on the same function, let me just do it once in general, and then I can just plug in the letters, the values for a after that. That's pretty nice, right? You guys see that? How much easier that is once you've got like the general form for the slope. Guess what? We're going to give that general form a name. You can say what? Don't listen to them.
Yeah. You're just like, what's up?
So when I do that, when I solve that for an arbitrary a, I'm going to define that as the derivative of the function f at that number a. And I'm going to give it this special notation. So I'm going to do f, and then I'll put a little like apostrophe on the f of a. That symbol, when we read that, that reads f prime. That's how you say it in words. So you'd say like f prime of a. Is everybody okay with that definition? And the other way we can write it again is using that other notation. Right? We had one of them where we're dealing with h and the other where x is approaching that value a. Doesn't matter which one you use. Depending on context, one of them may be more useful than the other, but they're both usable. Okay? I like the h1 in most cases. But there could be times where like the factoring that you have to do is such that the x minus a situation is a lot easier to deal with.
So what do you use like f prime versus not f, or are they just the same?
F prime is the derivative of f at a. So that's the slope of the tangent line to f of x at x equals a.
Okay.
Right? So it's the derivative of a function is like the slope of that function at that specific value of x. Does that make sense?
Yeah. Does the math change at all?
That we've done so far?
Like, if we use that formula on the derivative?
Nope. Nope. So let's look at example 4. It says, find the derivative of f of x equals yada, yada, yada at the number a. Let's do this then, right? So the symbol we use for the derivative, f prime of a, which derivative formula do you want to use? It don't matter to me. Which one do you think? I usually like the h1 too. I think that'll probably be easier in this case. Although there's no way for you to like know that just by looking at it without having tried it both ways. You know, like you have zero intuition right now about like what's going to be easy, what's going to be hard. That's okay. It's a point of like you have to do it for a while to develop the intuition. Like I can tell you, but that doesn't help, right? No, you don't. Usually either one will work. It just sometimes it may be like messier one way than the other, right? So we do this. Okay, that's the formula. So when I plug that in, I'm going to have a plus h squared minus 8a plus h plus 9 minus x squared plus, a squared plus 8a minus 9 all over h. Is everybody okay where all that gobbledygook comes from? Okay, you notice I distributed the negative sign through the x squared minus 8x plus 9, right? Very easy to forget to do that. If you don't understand where something came from, please speak up. You're not alone. Okay? Again, if I try to do a direct substitution here, I'm going to end up with 0 over 0. So let's FOIL. Yikes! Mr. Kulik, that got pretty messy. It's all right, let's see. A squared, negative a squared, you out of here. Minus 8a plus 8a, you out of here. Plus 9 and minus 9, you out of here. What do we notice about the terms that are left in the numerator? They all have h. Let's reduce those out of there. Boom, 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 boom. And then if we do a direct substitution, we have 2a plus 0 minus 8, or just 2a minus 8. So this is what f prime of a is 2a minus 8. So if I wanted f prime of 7, I can just plug 7 into a. If I want f prime of 92, I just plug 92 in for a. Everybody's cool? This is pretty nice, right? Can I point out the significance of what we've just done? We've created a new function, right? Whose output is a function, right? That taking the derivative operates on a function, outputs a function. Ooh, we've never seen that before, unless you count composition, right? You compose two functions, outputs another function. But this is the first time you've had like a one input thing that outputs a function. That's kind of neat.
So if you put any like value of a into that equation, it just gives you that, like the slope of the tangent.
It'll give you the slope of the tangent line at that specific value of x. Yes. Everybody's cool? That's pretty neat, Mr. Kulik.
That's really cool.
Okay. As we mentioned here, the tangent line to f of x at a comma f of a is the line through a comma f of a whose slope is equal to f prime of a. That is the derivative of f at a. So let's say it says find the equation of the tangent line to the parabola yada 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 at the point 3, negative 6. Do you recognize this? That was the function from the last one, right? Guess what we can say? F prime of a was just 2a minus 8, right? So my slope is f prime of 3. So that's just negative 2. And I just plug into point slope and I'm done. That's nice. Okay. A little bit of vocab here. When we talk about a difference quotient, we're just talking about the change in y over the change in x, aka slope, right? Now, instead of writing y2 minus y1, I wrote f of x2 minus f of x1, but that's fine. The instantaneous rate of change is going to be the limit as that delta, that change in x, goes to 0. Which is the same thing as the limit as x1 approaches x2. And this looks just like my derivative. So if we want to talk about an instantaneous rate of change, we're just talking about a derivative. Don't worry about the notation. The vocab is the piece that I'm concerned about. When you see instantaneous rate of change, whether that rate of change is a velocity or whatever, you're talking about a derivative.
Can you use the H formula?
Yes.
For that?
Yeah, that's an equivalent formula. Yep. Those two things can be used interchangeably. So, what's the takeaway? The derivative is the instantaneous rate of change with respect to x when x is 0, or x is equal to a, right? So derivative, instantaneous rate of change, mean the same thing. Slope of the tangent line, derivative, instantaneous rate of change, mean the same thing. Everybody's okay? That's the takeaway right now, is those three phrases. We've just got done showing that these are all equivalent actions. You're just doing the same thing. All right, Mr. Kulik. All right. So last example, it looks like. It says a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is f of x. What is the meaning of the derivative x, or f prime of x? Right? We've now attached real world values to x and y, correct? Is okay with that? So f prime of x is the derivative, so we say it's the instantaneous rate of change between what two variables? What is the y variable in the problem? The cost of production. With respect to, what is the x variable? And we should probably say X yards of fabric. Who here is in econ? Do you recognize this? This is called the marginal cost. So it's just the derivative of the cost function for production. So it's basically, what is the rate, like the rate in which cost production is going to change for each additional one more unit we're producing. Does that sound right, econ? Yeah, now you're speaking my language. All right. Part B says, in practical terms, what does it mean to say that f prime of 1,000 is equal to 9? Okay, econers, the marginal cost when x is 1,000 is 9. What is that saying?
Every 1,000 yards of average is 9.
Nope. So it means the cost to produce one more unit after 1,000 units have been produced is $9 per unit. So it's basically the 1,001th unit is going to cost $9, right? Econers, does that sound about right? And I guess the unit here is what? It's yards, right? Let's change that, I guess. So that's how much it's going to cost to produce the 1,001th yard. Typically, what do we expect as production goes up? The cost typically goes down, right? Until you've reached like your limits of production. Oh, it said what are the units? Okay. We did that. I guess we should. So this is, the units would be dollars per yard, right? So just the y unit over the x unit. Whenever you take a derivative, the new unit is going to be the y unit over the x unit, because it's just slope, basically. Instantaneous slope, but slope still. Which do you think is greater, f prime of 50, f prime of 500, or f prime of 5,000? What do we think? Econ students, we just said it, right? We'd expect the 50 to be the most, right? Because as production goes up, cost of production should go down. What could be the one exception? You've met like the limits of your production, would have to build like a new factory, then all of a sudden costs are going to go all kooky crazy because like, oh no, I have to build a new building and now that's astronomically more expensive and it doesn't get, I don't actually get a cheaper rate until I'm like at capacity at my new factory or something. You've met some new break-even point. Does that sound familiar, econers? I'm trying really hard to connect this to like other subject matters because calculus is one of the most versatile. Like we can really connect this to ideas we do in other stuff, whether it's physics or econ or biology or chemistry or whatever. All right. Our last example, I lied, there was one more. Says let D of T be the U.S. national debt at time T. The table in the margin, oh, I didn't give you the table in the margin. Way to go, Mr. Kulik. Let me drop that in there. Okay. Gives approximate values of this function by providing end-of-year estimates in billions of dollars from 1980 to 2005. Interpret the results, interpret and estimate the value of D prime of 1990. How would we estimate, can we calculate d prime of 1990? Let's start there. Is this table enough information to calculate an instantaneous rate of change? No, man, I can't do it. Can I estimate that, though? Yes. The way I would estimate that is I would use the slope. I would take the average of the slope from 1985 to 1990 with the slope from 1990 to 1995. And I would just average those two slopes together, and that'll probably be a decent estimate for the instantaneous slope at 1990. Is that okay? So if I do that, I get approximately $303 billion per year. So we've done the estimate. Now we need to interpret. What does that d prime of 1990 being approximately $303 billion per year, what does that mean? Let me start. In the year (1990), the what? What would I say? What is D talking about? The national debt. So D prime of D, I'm sorry, so D prime means the rate of national debt. Is everybody okay? So we just put that word rate in front of it if it's a derivative. And now is that debt going up or down? Up. How do you know it's up? Because the derivative is positive. So we'll say is increasing at a rate of $303 billion per year. Is everybody okay for that with what I did there? So again, if they ask you for a derivative and all you have is a table, your best you can do is give an estimate, an approximation of what it might be by averaging the two slopes is typically the way you would do that. There's lots of ways to make an estimate, but that's usually the easiest. It's just to take the two slopes on either side, average it together. Is that okay? So there's our problems for this. We'll do the 2-7 homework quiz next class and do the review stuff then after that. Any questions on what we did today? So again, the two most important things is that you're able to use those derivative limit definition, and that you equate instantaneous rate of change, derivative, and slope of the tangent line. All are asking to do the same thing, and that's that limit definition of a derivative. Everybody's okay? You want to hear a secret?
Sure.
That limit definition derivative is going to go bye-bye real quick.
Perfect.
And make this a way easier. And also kind of more complicated at the same time. But better than this. For example, in like 2 more classes, you'll be able to look at something like y equals x squared minus 8x plus 9 and do the derivative in your head. That's coming. That's coming. Which is super, super, super duper cool. So that's 3.1 when we do that. So we only have 2 sections of doing this like limit definition of a derivative before I start showing you the practical way of doing things. So hang in there. Don't read ahead.
Oh, no.
Don't read ahead. I know you're tempted. You're like, ooh, 3.1 sounds exciting.
Very excited.
Resist the temptation.